Hello everyone. So in this video, I'm going to start a new topic, that is bus admittance matrix, which is commonly represented as Y bus. So this is a mathematical matrix form representation of the power system network. So the entire power system will become a network, and in that network, I want to see what is the properties of the branches in the network, and I would like to represent that in the form of Y bus. And this Y bus is very useful in load flow studies, which is going to be the next topic after this. So let's get started with this. Before I begin bus admittance matrix, let me quickly review what we have, or just list out what we have learned so far. If you see, this video will be part of a playlist, and in this playlist, if you see, there are several other videos which are ahead of this, which are previous to this. And in that videos we had seen basically some power system basics. Then we have seen what is known as one phase AC circuits. Then we have seen three phase AC circuits. Then we have seen AC networks, and we have also seen one important topic, that is per unit system. This is per unit system of representation of a power system network, where the transformers are considered, and they using a system of per unit you can eliminate the transformers and make it as a common voltage. So these all are kind of stepping stones, and if you had not done this before, so please go back into this playlist and make sure that you learn all these topics before you uh, come to this topic of bus admittance matrix. Now in this topic, what we do is representation of power system network, of power network or power system network. So when you say network, so a network will have nodes and it will have branches. So let's say these are the nodes. So these nodes are typically like a power system network. These could be cities. So I can label the nodes A, B, C, D, or I can also give the numbering and so on. So these are called nodes. So while these are nodes, we have what is called branches. So consider this A, B, and C, D are all cities, each of them, and the cities are connected by a transmission network, which is a network of transmission lines. So just like a network of roads connecting different cities, we have network of transmission lines connecting different cities, and so on like this. So this is a network. So each of this transmission line will have some electrical parameters. It will have resistance, it will have reactance, it will have shunt capacitance, and so on. And these all parameters will form the network. Now, depending on the type of the city, so for example, C may be a generator. So there may be a generation plant at CTC. Of course, there will be some load also, but when I say C is a generator, I would say the generation is more than the local load at C. So it is actually sending exporting power, the CTC. So the power may go from C to D or C to E and so on. Whereas F also may be a generation city, and A may be also a generation city. Whereas B, G, E, and D could be load cities. There might be some local generation at D, but mainly the load is dominating. So I showed D as a load. So these are all uh, these are all loads. So if you think of a power network, it is just nothing but bunch of nodes which are connected by branches, and at every node either I'll have a load or a generator, and then uh, the network has to operate in synchronism, which means that at any moment in time, the total generation should be equal to the total demand on this network, uh, plus the losses that are going to be there in the network. So if you neglect the losses, if you think that there are no losses in the network, then the total generation should be equal to the total load. So just to give you an example, so let's say I am generating 50 kilowatts here and 50 kilowatts here and then 80 kilowatts here. So the total generation will be 50 plus 50 plus 80, that is 180 kilowatts. So total generation is 180 kilowatts. So again, kilowatt is just a unit I'm using. You can use megawatts, you can use uh, any other unit also for that. Then the loads could be something like maybe 20 here, 20 kilowatts here, 30 kilowatts here, and then 80 kilowatts here. So 20 plus 20 plus 30 plus 80, and then I think if this should be 30 kilowatts, not worrying about the losses. So if you assume that there are no losses, then total demand is also 180 kilowatts. Okay, losses are zero. Actually, there will be losses. We will see how to calculate losses and all in later videos in this playlist. But then a power system network typically is like this. There's a generation and then there is a demands, and the total generation is meeting the total demand. Now the issue is here the 30 kilowatts of load is there. So of course we are all talking about AC power system. So not only kilowatts, there will be kV kilowatts also, or reactive power also. So this is 30 kilowatts of load, and then plus j 10 kilowatt 10 kVA or of reactive power demand might be there here. So similarly the generation also, it's not purely active power, it could be generating reactive power. And similarly again, the sum of total active power should be equal to the total reactive sum of total reactive power generated should be equal to total reactive power consumed. But one point you should know is that this transmission line will have significant amount of reactants themselves. So a good amount of reactive power is also consumed by the transmission line. But it's okay, because reactive power, you don't require any fuel to generate reactive power. So active power you require fuel. For reactive power you can just generate it through different other means, reactive sources, or going for over voltage, over excitation of the generation, and so on. So ultimately you look at it, it's a something like a network where you're, so if I summarize it, it is nothing but a network. And inside this network there are bunch of generators generating power, and there are bunch of loads consuming power, and then the power is circulating through this. So for example 30, so maybe 12 kilowatts is coming from this C to D, and then therefore obviously by power law here, so the remaining 18 kilowatt should come from E to D, and 12 plus 18 will be 30 kilowatts. However, this number 12 kilowatt and 18 kilowatt should be determined by the network parameters. That is what is the load flow problem. We'd like to solve the load flow problem to know which line carries how much power, and whether the line carrying capacity of that line uh, is sufficient enough to carry that power or not. So these are the things that we worry about as power system operation. Similarly, here the load is 80 kilowatts, so maybe from here you are getting 70 kilowatts of power. So out of the 70 kilowatts of power, uh, 80 is consumed here, so 10 should be coming from somewhere else. Similarly, 18 should also be coming from somewhere else. So this will be 28 kilowatt. So if you apply again power law here, 28 is incoming, 70 is incoming. So total incoming power is 70 plus 28, that is 98. Out of that 98, 80 kilowatt is consumed here. So remaining 18 kilowatt is going towards D, where it meets the 12 kilowatt and then finally matches with the 30 kilowatts. So again, these numbers 28, 70, I'm just writing these numbers, but we have to actually calculate these numbers, and these are the solutions of the load flow problem which we are going to see later in future. So what are these power flows in throughout the network is what is the challenge, is what is the calculation that we'd like to do. Not only that, at every node there will be a voltage. So at this node, so now let me write the voltages. At node F, there will be voltage. So let's denote it as Vf and delta F. So you have already studied that the active power will flow from higher value of delta to lower value of delta. So therefore, Therefore, here, if I represent VE as the voltage and delta E as the angle, so in order for 70 kilowatts of power to flow from F to E, this delta F has to be more than delta E. So that the power is able to flow from here to here. So basically we need to adjust. So these are the unknowns. So this is unknown and all. So we have to keep adjusting and find out what is delta F, what is delta E and all. That is also in fact the main point of solution of the problem. Not only at these two nodes, everywhere. So at here the voltage may be VB at an angle of delta B, and here the voltage will be Vg at an angle of delta G, and so on. So I'm not writing it everywhere. So an n-bus system will have n different voltages and angles that needs to be determined. So of course, where there is a generator, you already know the magnitude of V. So for example, VA and delta A. So you know what is the magnitude of VA because there is a generator there. So you can set the voltage, how much you want to generate. You can just go to the generation plant and set the voltage, and you can generate the but then magnitude of VA. But then the delta A is still unknown. So these are some of the things that we are going to see in future. So basically, last 5 minutes or 10 minutes, what I am trying to discuss is how does a typical power system network looks like. When I say the power system network, it's nothing but bunch of nodes connected by bunch of transmission lines, and in between there are generators somewhere, loads somewhere, and finally the total generation. So this thing should match. Total generation should be equal to total demand, not considering losses. If you're considering losses, then let's say there are 20 kilowatts of losses and 180 kilowatts of load, then you need to generate 200 kilowatts of power so that the load and generation and losses, everything is in balance, and the system frequency is remain constant, and the system doesn't go into blackout. So system operates stably and all. Another issue is that, so here I'm writing 70 kilowatt as the power flow. So maybe the capacity of this line is only 60 kilowatt. So I'm overloading this line. So in the case of overloading of the line, how to alleviate that overload? The point that 70 kilowatt is flowing on this line, where the rating is only 60 kilowatt, is due to the physical parameters of the network, due to the Ohm's law and resistance and the impedance values and so on. So in order to control the power not flowing above the rated 60 kilowatt, the 70 kilowatt has to be reduced. So what you have to do is, maybe if I reduce this generation, instead of 50 kilowatt generation, if I do it 40 kilowatt generation or 30 kilowatt generation, by reducing this generation, I'm able to reduce this power flow on this line. But then if I reduce this generation, somewhere else I should compensate the generation so that the overall generation, load generation balance should be also be maintained. So what is, so this whole thing, whatever I'm discussing, is what is known as system operation. So system operation is done through power control centers. So a power control center is a place which is getting data from all the nodes to a central control room, where there is a big screen. On that screen, this network is displayed and all the power flows are displayed, and the operators sitting there, and also the software and hardware systems that are sitting there, uh, will try to manage the electrical grid without any overloadings, without any overheatings, or without any damage to any equipment, such that everything is operating in normal conditions. So that is the operation of system operation. So finally, this course, power system practice, ultimately comes down to how to do the power system operation. So anyway, we are going off topic. So let's get back to our main topic, which is bus admittance matrix. So why I have discussed all these things is, but bus admittance matrix, or what is known as Y bus, is the first mathematical step that you will take. I'm sorry, the first step is actually per unit system representation. So I would say the second mathematical step that you will take for representation of a power network mathematically in the form of a matrix. So let's see how it is done. So I'll for that I'll take a small example network, and then we'll see how it is done. So let me draw the example network here. So the example network is something like this. So I have I have four buses. So this is bus 1, bus 2, bus 3, bus 4. So just now I said node, but now I'm saying bus. So what is the this thing? So difference is nothing but node is a term that mathematicians use, and it is coming from graph theory, whereas bus is a term that electrical engineers use. So bus and node are basically the same thing. There is a line connecting 1 and 2, and the impedance of this line is Z12. So this is the notation for the impedance of the line connecting 1 and 2. There is also another transmission line connecting 1 and 3. By the way, this is a single line representation. There is actually a three-phase power system having a three-phase transmission line connecting bus 1 and 3, but then I'm just doing a single phase representation. And the impedance of this line is again denoted by Z13. Similarly, I have another line. This is Z1, Z34, and let's say there's another line connecting Z14, and then finally one more line connecting these two, and let's call this Z24. So what I have done is I have identified four bus bars or four buses or four nodes, 1, 2, 3 and 4, and they are connected like this. Now you know that each will have a voltage. So let's call this as V1, V2. So V2 means actually there's delta 2 also. It's a complex number. I'm not, the complex notation V1 is nothing but V1 with angle delta 1 and so on. So this is voltage is V3 and V4. So first what I want to do is that I have shown only the network. Now I have not shown where the generator is there and where the load is there. So for example, the 1 may be a generator, 3 may be a generator, and then 2 and 4 may be loads. So this is one combination. That means the power is going from 1 to 2, 1 to 4, maybe 1 to 3, 3 to 4, and so on. So these are different power flows that can happen if there is a generator at 1, 3 and load at 2, 4. Alternately, there could be a generator at 2 and there could be another generator at 4 and there could be loads at buses 1 and 3. This is another combination. The same network, the same parameter, the same voltage values or maybe different voltage values because the generations are moved. So now the power will be flowing from 2 to 1 maybe and then 4 to 1 maybe and so on. The location of generation and load is not important right now because I'm only worried about modeling the network part right now. Another combination, maybe there is a generator at 4 and all other places there are loads. It's not always required that there will be two generators and two loads. It could be any combination. So of course all loads, then there is no generation, then the power system cannot run. And then similarly all generators it can happen because all generators will be generating basically zero power. So that's another special case. Point is, right now I'm only interested in modeling the network, so therefore I'm not interested in modeling the different generators or loads at each bus. So I'll just remove that. However, I would like to denote, assuming that there may be some equipment here, I don't know, maybe it's a generator, maybe it's a load, something is there at 1 and therefore the current flowing here is I1. Similarly, something is there here, maybe a generator, maybe a load, and the current flowing is I2. Now you might say, why the direction is towards the bus bar? Why the direction is into the grid? So if it doesn't matter, it's just a direction. If there is indeed a load here, then the I2 will be negative. The actual calculated value of I2 can be negative, and therefore the current can actually, or the power can actually flow into the load. So we are not losing any, we are not introducing any error by assuming the direction to be inward. So what is this current? This current is I4 and this current is I3. Now you might also ask a question, what if there is nothing at bus 4? Bus 4 is just like a intermediate substation. There is no generation there, there is no load there. Also no problem, you can just substitute I4 equal to 0 and therefore that will take care of the system where there is no generation or no load at all these places. Okay, so in general, what is the definition of IK? Ik defined as net current injected at bus K from outside the network. Now Ik can be positive, Ik can be negative, Ik can be zero, whatever. But this is the key word here is this is the current injected and this is from outside the network. So that is about Ik. Now I can write it in the form of a matrix. So because the size of the system is 4, so n equal to 4. So n is typically the variable we use to represent the size of the system. I'm using n equal to 4. So sometimes for a practical system, n can be 1000. There could be 1000 system, 1000 node electrical network also for a very large network, or it could be even more than 1000, maybe 5000 or 8000 or whatever. But for our example, I'm just doing a 4 node system. Then I can write it as a I equal to I1, I2, I3, I4. So I can write it in the form of a matrix where all the current injections are represented. So this is the, and the size will be n rows and 1 column, n cross 1. So in our case it is 4 by 1. So this one, let's call it as bus current injection vector. So I1, I2, I3, I4 is the matrix of current injection. These are all complex numbers, I1, I2, I3 and I4. Now also I have already indicated V1, V2, V3 and V4 are the voltages. So therefore I can represent V as a matrix. So this I is a matrix and V is a matrix. It will also have V1, V2, V3, V4. Each of them are complex numbers, and this one is the voltage vector, bus voltage vector. And of course the size will be n cross 1, and in our case right now it is 4 by 1. It could be 5 by 1, it could be 100 by 1, it could be 500 by 1, depending on the size of the system that we are studying. Now we can ask a question, what is the relation between these two matrices? So the relation will be something like this. I equal to Y V. Now Y is a matrix that is actually our bus admittance matrix. What will be the size of this? So n rows and 1 column, and this is n rows and 1 column. So therefore this should be n cross n. Then the size will match. So basically what we are looking for is, if I know what is this Y bus, then this is my network representation. So then depending on the injections, the voltages will change. So if, but this Y bus will be just simply the relation between the voltages and currents. So so if I inject more current, how it will affect the voltage at V4, how it will affect the voltage at V3, and so on. That determined by the this Z12, Z13, Z14 and all these parameters. So I hope until now you have understood the notations. What is this I bus? What is this V bus? I bus simply the external current injections. External bus current injection vector I1, I2, I3, I4. And then Y bus is this V is nothing but V1, V2, V3, V4. These are bus voltage vector at all the buses. And the relation between them is this, and this matrix is actually bus admittance matrix. Also denoted as Y bus. So already you know one thing, what is the size of this bus admittance matrix is n cross n. So on. Okay, so for our example problem that I have shown here, the Y bus will be 4 cross 4 matrix. Anyway, we will stop this video here and we'll continue in the next video. and I'll try to derive, or I'll try to find out what are the elements. So there will be 16 elements inside this Y bus. 4 into 4 is 16. So I want to derive each and every element of this Y bus. How does it look like? Because given these values, Z12, Z13, and so on, I should be able to find out what these values are. It's just simply applying Kirchhoff's current law at each node. We'll be doing that soon. See you in the next video.